Good afternoon. It's my pleasure to introduce Chris Monroe as a speaker today for Quantum AI Tech Talk series. Chris is one of the leading atomic physicists and quantum information scientists in the world. He's well known for his pioneering work on trapped ions and his famous experiment on first quantum logic gates in 1995. Which actually led to Nobel Prize in Physics in 2012, which was shared between Dave Weiland and Serge Haroche. Chris moved to a University of Michigan as a faculty in 2000, and he managed to put the trapped ions on integrated semiconductor chips. And then in 2007, he went to University of Maryland and demonstrated the first quantum teleportation between two quantum matter over distances of on the order of meters. And he's right now working on modular quantum computing, quantum devices, which he's going to discuss it with us. Let's thank Chris for today's talk.
Thank you, Masoud, and also Hartmut for having me here. And in the course of this time, please feel free to interrupt me with any questions. It's a slightly different audience than I'm used to, but I like speaking to audiences that may not even have any knowledge of quantum physics. That's actually maybe an easy audience. But here I'm going to dig sort of deep into a particular technology. And in the course of doing so, try to make connections to any type of a technology, paying attention to certain aspects of quantum technologies that will be required to build a large-scale system. And so maybe the first example, I don't know, is there a laser pointer in the room? Sorry, I should have brought my own. I'm a laser guy. Oh. Okay, thanks. Okay, kind of weak, but. So there's a question on who is this Boris guy. Well, when I was at Michigan, he was one of my postdoctoral researchers, Boris Blinov. He's now on the faculty in Seattle, University of Washington, and he's a very good painter as well. And this is an oil painting. At the time, we were playing around with an atoms of cadmium ions. And if you've ever dabbled in oil paints, you know that this bright yellow hue is called cadmium yellow. So he painted this to represent two cadmium ions, and this in between presumably is the entanglement between the two cadmium ions. So you can use your imagination there. This hangs on my home office wall. My wife doesn't like it so much, so it's banished to my own space. Okay, so as an example of something I'll talk about that doesn't pertain just to individual atoms, which I will be talking about at length, I want to talk a little bit about qubit economics. Okay, so I made up this slide, so if you don't agree with it, you can yell at me and throw things. But one figure of merit of whether you want to build a quantum computer or if you're going to build a quantum computer, how big should it be, is how much will it cost. And here on the x-axis, I've labeled the number of bits. And of course, in quantum computing, bits are quantum bits that have this funny feature of being able to exist in both states, 0 and 1 at the same time. And well, one quantum bit's very cheap. In fact, it's trivial to deal with one, so I didn't start there. I started at 2. And this is the cost per qubit. And so I guess I would propose that any technology, may be wrong, the precise shape and where the knees and the bends are here, and where this sort of asymptote is, but it seems to me that most qubits sort of will start off fairly expensive. You can put whatever dollar figure you want there, and then the cost will grow, but at some point it will saturate. If I give you 50 qubits, I probably could have given you 51 at very little added expense. And so that's this nice area where we want to scale things up, and naturally we're going to push that until the slope starts growing. Now you might know in classical computing, in fact, the slope can be negative. When you build more bits on a chip, the cost per bit can be less, and that's of course one of the ways to describe what Moore's law is, meaning that things have just gotten much better over the last 50 years or so. but we all know that time is ending. And in fact, quantum computing is sort of a revolutionary change to the fundamental rules of computing. So Moore's law doesn't necessarily apply to this model of computing. And so we might not expect classical curves, cost per bit, to be the same as quantum. I guess the most important point I want to make here is that, well, in addition to this flat zone, there will be at some point, when you put too many qubits together, it gets very expensive to add that next one. The system just gets too big. It gets so big that if you want to maybe reduce things, they become classical. They lose their quantum character. We sort of know this in physics. Any very big system, quantum mechanics really doesn't play a role anyway. This is a pretty small system, maybe 100 qubits or so. But in many technologies, this number will be different. Depends on the technology, depends on the state of the art, depends on all kinds of engineering processes. And it seems that some technologies that are talked about now, this need does happen on the order of 50 to 500 or something, okay? And so in addition to this plot, I suppose we should plot other lines of constant dollars. So since we're talking about the cost per qubit, these curves sort of go down with the number of qubits. So if you have $1 million, the cost per qubit better be small if you're going to make a lot of qubits. And the point, of course, is where these lines cross is how big of a system you'll be able to build with a certain budget. And of course, when you have a vertical asymptote, it means it doesn't matter how much you spend, you're stuck at 100 qubits. Okay. And again, this is not a physics lesson. I guess I can't prove that physically everything has to be this way, but in practice, I believe this is the case. And so it turns out that I think in the foreseeable future, we'll be dealing with quantum systems that are on the order of hundreds of qubits or something, which is not so big, but of course, that's not the only story here. If you have only a few hundred qubits and you want 100 million, you have to figure out somehow how to modularize the system, make it multi-core in a way, and adopt concepts from classical computing architecture. And that's not my field at all, but I'm always a student, and like many of us in this field, we will learn from high-level computer architectures. And of course, this is a big topic in the quantum group here at Google, very interested in these issues. Okay. With that editorial and speaking on something I know very little about, this is total guesswork, of course. I think it's not too far removed from reality. I'm going to move on and talk about hardware. Are there any questions yet? Hopefully not, because I probably can't answer them.
Also, make a question, because that's how everybody go to the mic.
Okay. Any question? Somebody come up to the microphone right in the middle then. Okay. And again, feel free at any time to rush up there and yell at me if you want. Okay. So let's get into hardware. And as Masoud mentioned, I've been involved with this field for a number of years now, and in the last few years, things have really changed, and I think this is maybe typified by the fact that we have now pretty much two technologies that are starting to separate themselves from the rest of the field. So what is a quantum technology? A quantum technology is a system that can be sufficiently isolated to store superpositions of values. Now, the laws of quantum mechanics tell us that superpositions are fine. We can store any quantum attribute can be prepared in a superposition of states as long as you don't look, as long as you don't measure, as long as the environment is not influencing the system in a way that we can't compute. So in quantum mechanics, we typically talk about the fiction of an isolated system. You know the analogy to Schrodinger's cat, the cat that's both dead and alive. Well, to me, what's strange is not the cat being dead and alive. What's strange is that the box that the cat sits in is totally leak-free. Nothing observes this cat. There's nothing from the outside environment that can get in. And that's the hard part. That's the hard part. And it's the weird thing in quantum physics that we can think of isolated systems. Now, in the laboratory, nothing is perfectly isolated, but it can be sufficiently isolated to do things, to do interesting quantum computations in a time that's much faster than it takes the environment to leak in. So as I mentioned, these two technologies, individual atoms that are held in a vacuum chamber and superconducting circuits of wire at very low temperature, these look really interesting now, and we're seeing efforts to build systems at a fairly sizable scale, approaching hundreds of qubits and so forth. And here I point out some of the state-of-the-art and positive sides of these different physical systems, and also some of the problems. And what's neat about these two platforms is that they're somewhat complementary. Superconducting circuits can take advantage of existing fabrication technologies. You can order 1,000 qubits to be printed on a circuit board. Of course, wiring them up is another matter. It's very difficult. Things have to be held at very low temperatures. Atomic ions, on the other hand, they don't come with wires. You get to wire them up externally with laser beams. That's good and bad. It's good because we can reconfigure the connections. I'll talk a little more about this top platform, of course. This is what I work on. So you can wire them up in a reconfigurable way, but it requires lasers. It requires lasers that have low noise and so forth, and these are fairly exotic types of hardware to imagine in a computer. Whereas superconducting circuits involve radio frequency sources, sort of conventional currents and voltages that we all deal with, that conventional computers deal with. Superconductors have to be kept at very low temperatures. The whole chip and the surrounding has to be held at millikelvins above absolute zero, whereas trapped ions, they can work in room temperature apparatus. We probably want to go to 4 Kelvin for technical reasons, but they have to be in a vacuum chamber. So it's like we've gone back to the days of vacuum tubes. So what you should take away from these two comparisons is that whereas superconducting circuits are somewhat exotic compared to CMOS, these trapped atomic ions are really exotic. This is hardware that lacks an engineering presence that we have in superconductors. And so it's no surprise that of the big investments in quantum computing in the last few years, this is probably not an exhaustive list, but what's notable is that there have been several very large investments in particular hardware. On the superconducting side, of course, the collaboration between this office and the group at Santa Barbara is quite notable. IBM itself is investing heavily in this field. Lincoln Labs up north of Boston has a smaller effort. But these are big efforts really devoted toward building something up. And this is something new in the field. Now, on the atomic physics side, most of this work, in addition to university-style research, is funded through the government at this stage. And while Lockheed and Honeywell and a few private outfits are starting to look at this, it's still, we're still going to lag, I think, a few years behind superconductors. I think both of these technologies, though, will sort of, I think, learn from each other right now. And I'm going to now move on and talk a little bit about this exotic type hardware. Maybe you haven't heard about it too much. I do mention at the bottom here, there are many other quantum platforms that look interesting, but I would say they're still in the exploratory stage, the researchy stage, where, say, atoms and superconductors were 10, 20 years ago. Yes, question?
You said they complement each other. How's that?
Oh, thanks. I should probably expand on that a little more. Well, the one thing about superconducting circuits, this is sort of a cartoon of one superconducting junction. You simply wire them to neighbors through capacitive wires or inductive couplings and so forth. They're typically printed out on a two-dimensional chip, and you have nearest neighbor interactions represented by wires between nearest neighbors. You can do slightly more than that. So the connections are hardwired. You can't change the graph without changing the chip. Trapped ions, on the other hand, they can have an all-on-all coupling. They can have long-range interactions, very long-range interactions. They're reconfigurable from the outside. And so already that implies that maybe the application of this hardware might be different than the application. So in that sense, they're complementary. I didn't mention speeds and so forth, but superconducting circuits, they can execute gates fundamental operations at the nanosecond and faster time scale, very fast. Atomic systems are, with a single exception I might note in a little while, are quite slower, on the order of microseconds or even a little slower than that. The memory times, the coherence times of superconducting qubits is typically microseconds, but again, there's a big spread depending on exactly how they're connected. I don't write the time, well, I guess I do here. These atoms, they're the same isotope of the same element, and they're basically atomic clocks. They're incredibly good memories. There's really nothing. They're standards. So they have very long memory times. So you could imagine, I mean, in the long run, I could look 50 years in the long run, if none of this other stuff develops, you could imagine the superconducting systems doing fast computations and the trapped ions being the memory. I don't know. That's maybe a long shot because you have to somehow couple them in a quantum way. But in that sense, they are complementary. Maybe the most important thing is that there's a lot of engineering. There's VLSI of these things. We don't have any of that in atomic physics. We don't have the engineering. Okay, so let me talk about trapped atomic ions. So here's a picture. Now you can see already this wasn't very well engineered. Well, actually, I think it was, but it was clearly hand assembled. Here we have a bunch of electrodes inside of a vacuum chamber. That window is 4 inches across. This steel thing is it's a microscope objective, 1 inch in diameter, and it is imaging a bunch of atoms that are held in this gap right there. So these are gold electrodes that were plated on a ceramic substrate. There's a couple layers of them, and you can see the wires. This is not Intel's work. This is our work. This looks like a university laboratory, doesn't it? But when you apply appropriate voltages to these electrodes, you can create basically a potential that will store charged atoms in free space. So these atoms are hovering in free space, which is a great ingredient for a qubit because that means they're isolated. There's no surface. There's no gas. It's a vacuum chamber. There's very little gas. It's not a solid. It's an atomically perfect little crystal here. And here we have, this is a picture, maybe it's a ½ a second integration on a camera of about 15 or so ytterbium atoms, ions, ytterbium plus ions. Now, each atom here is separated from its neighbor by several microns, and this is just a compromise. We're squeezing them together, but they repel each other. So they form an equilibrium spacing. You'll notice, first of all, the spacing is not uniform. That's sort of not a big deal in the long run. We know how to make them uniformly spaced, but there's no need to for such a small system. Secondly, the reason you see these atoms at all is that we're shining lasers on the atoms, and they're fluorescing. Now, atoms are unlike solid matter in that atoms are very discriminating. They only respond to very narrow bands of color. And in fact, this light here is in the near ultraviolet, and we have to tune, stabilize, and make accurate the wavelength of this laser to about 9 digits of accuracy every day. And this is a lot of the classical control that goes in the back of one of these atomic experiments. We're seeing here diffraction-limited spots from a bunch of point sources. These atoms are very cold. They're laser cooled. I'm not going to talk at all about that. They're laser cooled to very low temperatures, and they form this linear crystal. And each atom fluoresces very strongly, but the fuzzball here is given by the diffraction of this lens. So the atoms are actually about 1,000 times smaller. That's exaggerating. About maybe 300 times smaller than this blob, but because of the diffraction, they're sort of spread out in space. So don't think of this as the electron cloud. That's basically just a single. It's like looking at a star in a telescope. You have some resolution limit. But fortunately, it's enough that we can discriminate. We can label these and call each one a qubit, and we can manipulate them optically with other laser beams. And I'm going to talk a little bit about that. So let's go inside one of these atoms. Atoms are complicated. Yeah, question.
So what's the uncertainty in one of these atoms' position? How does it compare to the size of the blob?
The size of the blob is about 1 micron, and the uncertainty position is about 1/100th of that, about 10 nanometers.
Okay. So comparable to the atomic radius itself, or no, it's bigger than that?
It's quite a bit bigger. It turns out the fundamental limit here is also given by quantum mechanics. If we know where an atom is, it must have residual energy, velocity, and that compromise gives us a minimum spread in position of a few nanometers.
Okay.
And fortunately, that parameter doesn't really play a role in anything we talk about. All we need to
And
do
what is the atomic radius?
the atomic radius for most
is in
atoms
picometers?
is typically 1/10 of a nanometer or so.
Okay.
Okay. Yeah, you know, I would call myself an atomic physicist, but I very rarely think of the atoms as more than just a 2-level qubit or other levels that we use. But yeah, the motion, the electronic motion of all these inner core electrons doesn't matter. Now, I also list a bunch of groups here that are doing research involved in trapped atomic ions. And I like to point this out. There are maybe 30 or 40 groups in the world playing around with this system with research involved in quantum information science. Because 20 years ago, even 15 years ago, there was only one group doing this. And this was a group I worked with Dave Wineland at NIST in Boulder. And since the mid to late 90s, since quantum computing really took off, this field has exploded. Mostly at universities, but not entirely. There are groups in industry, for instance, at Honeywell and at Lockheed, and government laboratories like Sandia National Laboratories and Georgia Tech Research Institute. But the field is growing explosively over the last 10 years. Okay, so let's look inside one of these atoms where we store the quantum information. Well, it turns out ytterbium, I won't get into too much atomic physics except to note that ytterbium plus, you might ask, why this atom? Well, ytterbium plus is a very simple atom in that it has only one outer electron. All the inner electrons are paired up, and we don't excite those, so I think of those as sort of frozen out. Now, the nucleus has lots of protons and neutrons, but their spins are also paired, so the whole nucleus effectively has a spin 1/2. So the nucleus is a qubit. This outer electron is a qubit, 1/2 and 1/2. So it's exactly like that of an isolated hydrogen atom. And as such, the atomic structure is exactly like that in hydrogen. And so here, the vertical axis denotes energy, and the horizontal axis are just different states. And this is the so-called ground state hyperfine splitting in the ytterbium ion. You can tell I'm a physicist, not a computer scientist. I label this as up and down instead of 1 and 0. But you can think of this as the qubit state 1 and the qubit state 0. Now states, these two states in the atom represent their so-called hyperfine levels. Think of them as different states of spin of the nucleus and electron taken together. Now, it turns out that exactly these types of states currently define the second. So this is basically an atomic clock. And the reason it's an atomic clock is that this energy splitting is very well defined. It's the same here in Los Angeles as it is in Washington, D.C. You can take your own 171 ytterbium ion, and you will measure 12.6 gigahertz, 0.6428, 12, 118, et cetera, gigahertz. It's very well defined. It's a standard. And also note that there's atomic physics in these two particular levels. They don't shift very readily with external perturbations. This is an ion. It spends its time in zero electric field, so there's no electric field shift. And also, it's very well shielded from magnetic fields. Turns out, with laboratory magnetic field noise, the coherence time of these pair of levels can be as high as several seconds without any work, without any shielding. If we want to go to 15-minute coherence times, we could easily do that. It has been done. We don't need to because all of our operations are much faster than a second. Okay, so there's the qubit. Within each atom, think of it as a spin state inside the atom. Okay. Well, in addition to storing quantum bits, we can also measure the state of a single quantum bit or many quantum bits. And this is very straightforward, in fact. It's simply you shine light on at a particular color. One state glows, the other state doesn't. And so the atomic physics here is that when we shine laser beams, in this case, it's in the near ultraviolet part of the spectrum, this spin-up state, it turns out that we can excite the spin-up to an excited state, and it returns right where it started. And it does it again and again and again. It's sort of like an amplifier. And this is real data on a camera, the image of a single atom prepared in spin-up, or 1 if you want. And this is a collected histogram of the number of photons we collected on a simple photomultiplier tube in half a millisecond. And this is several hundred experiments. We see an average of 10 clicks when we're in the state up. And if we're in the state down, the same laser is 12.6 gigahertz away from this line. And this line only has a width of 20 megahertz. So the point is the atom is largely transparent if it's in the state down. And here's data, same experiment. The only difference is we prepared the atom in the other state. So you can clearly see a good detector here. Even in a single shot, if we see light more than one click, that's background light or something, or just small errors on the detector, dark counts. If we see more than one click, we can be sure with very high probability that the atom is in the state 1 or spin up, and if we see 1 or 0, it's in the state down. Now, we typically measure 99% discrimination here. There's a slight 1% overlap of these distributions, but we can get to 4 nines of this measurement without too much extra work. Again, we don't need to yet. When we have hundreds of qubits, we will. Okay. All right, so that's sort of the background in the qubit and its measurement. Well, how do we do something interesting? How do we make superpositions? How do we make logic gates? Well, you need qubits to interact to make a logic gate. Like an AND gate, it requires 2 inputs, and the output depends on the states of those 2 inputs. Well, these atoms don't naturally interact very strongly. The qubit states are spin within the atoms. And 5 microns is actually miles away, atomically speaking. So whether one atom is up or down, the other one doesn't really care. But what is strongly coupled is the motion of the atoms. You should think of these atoms as a bunch of masses connected by springs. If you move one, then they all know it. And this is exactly the interaction we use to do something interesting. And we do this again with laser beams. And in this case, the laser beams, I don't want to get too bogged down in the atomic physics here. The laser beams don't couple to an excited state and cause fluorescence. They are detuned from any excited state. So they don't directly scatter off the atom. But we apply 2 laser beams that have a precise difference frequency matching or very near this number here, 12.6 gigahertz. When we do that, in fact, there's a coherent transition. We call it a 2-photon transition. There's a coherent transition between up and down, and we can do this sort of in the dark. It's not a measurement. It doesn't tell you whether you're in one or the other. It just flip spins. This is sort of a very simple way of doing a gate, like a NOT gate, flipping a spin coherently. Or in quantum mechanics, we can do something called the square root of NOT, which has no place in classical gates. A square root of NOT is that gate which, when applied twice, is a NOT gate. So we can flip this spin. We can do a cube root of NOT and so forth. And that just depends on the power and the time of application of this laser beam. So you can already see right away what I hope you see what the bottleneck in all of our experiments are. It's this laser, controlling it, controlling its power, controlling its spectrum, controlling that it doesn't point and move around on these individual dots. Okay? Now, one really nice feature of the ytterbium ion is that this detuning, by the way, it's not drawn much to scale. It should be about 1/3 of the way between these two. For technical reasons, that's sort of the optimal place to work between these 2 excited states. I didn't even define them. Doesn't really matter. And it turns out for this particular atom, that wavelength is very friendly. It's 355 nanometers. You might not know what that is, but it's the 3rd harmonic of a very popular color that's used all around. And in fact, that color is used for all nuclear fusion experiments, laser confined fusion. And the reason it's popular, this is slightly different, it's not 355, but it's based on a particular nonlinear crystal that works very well called the YAG crystal. If you've ever seen a green laser pointer, that's the 2nd harmonic at 532. So here we have a pretty big laser at Livermore Labs. And the point here is that you can get as much power of this laser as you want to pay for. Now, we don't typically use the megawatts of power they have at Livermore. We instead use a much more modest version. This is a few feet across on the table. But it produces laser pulses, and I'm not going to get into the details, but this is that one example of doing very fast operations on atomic systems. We can control a single atomic qubit at tens of picosecond type timings. It's, as long as you have enough power. And this takes a few watts of average power to do that. Okay. So I think I've given you all the tools then for how we how we manipulate, measure, and store quantum information in atoms. Now let me give you, after, let's see, I'm about halfway done. Now I can give you my outline, which is basically how to wire them together and how to make a system big. I'm not going to talk about all these in great detail, but I will talk about one, this top one. Again, the natural way to wire them would be through their Coulomb interaction, their repulsion. And let me give you the very high-level view of how a quantum gate works involving the Coulomb interaction. Okay, we have a bunch of atoms here in a chain, and let's say we want to do an AND gate or some type of a quantum gate between any two of these atoms. Well, here's what we do. We shine two laser beams that only hit the two atoms in question, and these laser beams are tuned in a very special way that allow us to apply a force to the atoms. It pushes the atoms, but very importantly, it pushes the atoms in a direction that depends on their internal state. And this can be done based on selection rules of the atomic transitions. And we do this with our 355 nanometer lasers. In this example, if the atom is in the state spin up, it gets pushed upward. If it's in the state spin down, it gets pushed downward. These are called optical dipole forces. They're very well known. And there's some displacement, delta, in space between the two, up and down. Now, the physics, what's happening here is that we're going to consider the energy change between all four configurations of these two spins. Okay? Now, if they're both state spin up, they both move up together. The Coulomb interaction is the same as it always was. They're the same distance apart. If they're both spin down, they move down together. So the Coulomb energy doesn't change. And for the moment, we're going to forget about all the other ions. That's actually, in one limit of this, that's fine. Just forget about those. But if those two atoms are different states, down up or up down, they're a little further apart from each other. And it's that tiny change of distance that modulates, that changes their Coulomb energy that allows us to do an interesting operation. So if you look at the math here, the change in energy, this is the Coulomb energy from when they're on this little diagonal here minus their original Coulomb energy. And this is the expression. And in physics, this is known as a dipole-dipole interaction. We have an effective electric dipole. Charge of the ion times the separation squared divided by r cubed. And these energies can be very large. And this is exactly what we use to do gates. Why is this a gate? Well, if you look at the four configurations of those two spins, again, only the two mixed states suffer this energy change. And in fact, it's the same energy change. So in quantum mechanics, we add this phase factor. The energy decreased a little bit for a certain amount of time. And so that determines this phase factor. And when that phase factor is pi over 2, these two numbers here in front are minus I. And it turns out that's equivalent to a controlled NOT gate or a NAND gate. It's the sort of bread and butter of the gate model of quantum computing. It's a universal gate when taken along with other more trivial gates. And so this is the physics of what's going on. We're applying forces to these atoms. Okay? Any questions on that? There are many different regimes of this. This is one particular. I didn't want to get too detailed, but this was first pointed out, by the way, only months after Ignacio Serac and Peter Zoller learned about Shor's factoring algorithm. They're atomic theorists, and they learned about this math breakthrough, and they said, well, look, there's an atomic system that actually we can develop gates for. And it's been refined and improved over the years, and many laboratories now operate gates like this on small collections of ions, including our lab. And in our lab, we've made a lot of progress by not focusing on individual atoms, but do something a little easier, and that is just hit them all with the big fat laser beam. Then you don't have to worry about the focusing and turning on and off of individual beams. Now in this case, we're applying a force on every one of these atoms. And let's say it's the same as I mentioned. If the atom's state spin up, it goes up. If the state spin down, it goes down. So this force, remember, it has this funny form. This means that if you're in the state spin up, you have a plus force. If you're in the state spin down, you have a minus force. And so an interesting question here is, it's not exactly a quantum computing question, but it's more of a physics question. What is the configuration of these qubits the spins if you want, what is the configuration that minimizes the energy under the influence of this force? Okay. So if they're all, remember, if they're all spin up, they're just going to all move up together, same energy. If they're all spin down, they're going to move down together. So the energy doesn't change there. Well, it turns out this configuration where they're alternating, up, down, up, down, up, down, it's not too hard to show that this minimizes the energy. And you can kind of see all the atoms are on average a little further apart from all the others. You have to do a complicated sum to show this rigorously, but it's true. Slightly more interesting is that there's another state that's equally low energy, and it's this one, the other guy. So these are two states. These are so-called Neel-ordered states of an antiferromagnetic Hamiltonian. Antiferromagnetism means that neighboring particles anti-align. And it turns out, you might imagine, if we make this state in the right way, we might have both of them at the same time, since they're both the ground state. So this is maybe an interesting place to think about doing some physics. Now, of course, this force here doesn't flip spins at all. So you're not going to find the ground state by just applying this force. You have to somehow mix the spins around. And this is afforded by applying a so-called transverse magnetic field. So depending on the relative strength of this magnetic field and the force, the atoms will either sort of spin around the magnetic field or they'll align according to this force. So this term sort of allows you to mix and sample the entire space of spins. This is a very fundamental model in physics. It's called the transverse icing model. It's sort of the first thing you learn in solid-state physics. And it's the simplest quantum model that admits a phase transition, a quantum phase transition. So it's actually a good place to think about doing some experiments. And indeed, experiments have been done. There's sort of a little cottage industry of simulating magnetic spin models in trapped ions, starting from the theoretical proposals, the same Serac and his collaborator Diego Porras. And many years later, we see a whole slew of experiments. About half of these are from our group. Since I'm running out of time a little bit, I want to. This slide is so busy, I'm not going to get into it in much detail, except to note that the force we apply for technical reasons is at a right angle, and it creates sort of a running standing wave over all the atoms. We don't gently push the atoms up and gently push them down. We push them it's a time-varying force that is near the normal mode frequencies of this chain. And that gives us a big resonant enhancement. And all I want to do is point to the end of this nasty math, in that we end up with this icing model, which is a coupled spin model here. And the coefficients that couple spin I and spin j are basically all on all. Every spin talks to every other spin. So this is a so-called long-range model. It's not a nearest neighbor only model. And there's some math behind this, but the coupling matrix between spin I and j depends on laser parameters. We can tune the power and the tuning of that laser to change the configuration, change the model, even change the range of the model, how long range the interaction is. So this is sort of a test bed to do what are known as adiabatic quantum simulations. In this case, this is a cartoon from one of Seth Lloyd's papers many years ago. The idea is to prepare a bunch of spins in a trivial ground state. In our case, we prepare it in the ground state of this part of the Hamiltonian. This is the transverse field. And then we hopefully adiabatically turn on this part of the Hamiltonian. What does adiabatic mean? It means that it preserves the entropy. It doesn't add excitations if you want. So if you do this adiabatically, you turn B down to 0 and J up from 0, then you should evolve to the ground state, the lowest energy state of this model, which can be interesting. And this is the so-called adiabatic model. And experimentally, we lower the magnetic field according to some profile, and we turn on the icing coupling. And at the beginning, B is much bigger than J. At the end, B can go almost nearly to 0, whereas J is still on. And again, I'll note that these icing couplings, they fall off with distance with a polynomial, a power law. And this power law can extend over the whole chain or over just a few neighbors. Okay. And I just want to give you a brief glimpse at some some early data on this type of a simulation. This is with only 10 spins, though. And remember, 10 qubits is only 2 to the 10 states. So there's 1024 configurations. That's not big enough to be earth-shattering. 2 to the 10th, we can diagonalize 2 to the 10th by 2 to the 10th matrices. Nevertheless, the whole point here is scaling up to much larger numbers where we can't. And it turns out that number is more like 2 to the 30th. So we're not, with 10 qubits, we can model everything on a PC, or a fancy PC. With 30 or 40, we certainly can't. And so everything here is premised upon doing something better in the future that will put us in a land where we can't simulate what's going on. Okay, so here are a couple of images of 10 ions. Here they're the calibration. They're all in state up. Remember, they're bright in state up. Here they're all dark, state down. Well, we did this experiment 2,600 times, the same experiment. We tried to adiabatically, we prepared the atoms along a transverse field, and we tried to adiabatically lower the field so that we were prepared in the ground state of an antiferromagnetic icing model. In fact, the range, the power law was 1. In other words, the interaction fell off like 1 over distance to the 1 power. Fairly a long range, but not infinite range. Well, out of those 2,600 runs, we found about 17% of the time we got one of these 2 states. This is a very direct measurement, by the way. Every time we do an experiment, we simply shoot the laser and see which atoms are bright, which are dark. And we can directly measure the quantum state. Here we have the expected Neel ordered, one of them. Here we have the others, and they're roughly half and half. But this is only 17%. What happened to the other 83%? Well, we can look. We can see exactly what happened to the other 83%. Well, here's 8% of that 83%. It sort of looks like Neel ordered, except we have a domain wall. And these four levels are actually degenerate. They're expected to be. And so 8% of the time we had these states. These are excited states. So we were not adiabatic, apparently. We made excitations along the way. Here, the next excited states, 1% each, the domain walls moved further out. Okay, so the dynamics of this experiment are actually really difficult to simulate. We weren't adiabatic, but simulating exactly what's going on is a little tricky, even with just 10 spins. So here's a distribution of all 1024 configurations and their probability. Since we started with the transverse field, this is up plus down to the 10th power. We have a superposition. Well, yeah, we have populations of 1 out of 1024 in each configuration. And then after the simulation, we see these 2 states, also known as 341 and 682 in decimal. They pop out, and again, they represent together 17 or 18%. And then you have all this other stuff. This is real dynamics, and there's a lot of physics in what populates those states, and that's sort of interest in the long run. Now, what about scaling up? Here's the same experiment with 14 spins. This time there's 16,000 configurations, and we're paying the price already. We only see the ground state, I don't know, 3 or 4% of the time. What's happening is the gap is shrinking, and we're not going slower. We should be going slower and slower and slower, and we're not. So again, this is a little bit of a taste of sort of what we're playing with right now, and again, I'm sort of running out of time, but we're having a lot of fun engineering various types of Hamiltonians in a small chain of between 5 and 20 spins, including studying spin 1 dynamics instead of qubits, having 3 levels. That has actually some import for topologically encoded qubits. So well, why are we, you might ask, why did we stop at 20? Why didn't we just go all the way to 100, where I claimed that cost function goes through the roof? Well, it turns out this is a technical shortcoming of our current apparatus. Remember I said vacuum. Well, the vacuum's not perfect. There is a background gas. And it turns out every atom that we trap in this system suffers a collision with the background gas about every half hour at our pressures. That means that if we have 30 of them, the whole crystal will melt every minute. And it turns out it takes about a minute or 2 to recover from that. We don't lose them entirely. We just have to recool them. It takes a few minutes because we're not very smart at it at this point. But that means that we're never taking data, because by that time another collision happens. So we're limited by a background pressure to about 20 spins. So in the future, sort of know how to get around this. The apparatus is room temperature, but by going to 4 Kelvin, and this is a picture of the cryo system we have, and there's a cartoon of our next generation trap we'll install, we should be able to get pressures that are about 10,000 times better, maybe only 1,000 times better. But the point is, when we store a crystal, then we're basically shutting off the background collisions. Now a crystal will last for months. It should. And of course, we have to set this thing up. And so we're well on our way. In fact, Phil Rescherm's in the audience here. He's a postdoc in the group and a research scientist who designed this, and Paul Hess has come along, and he's going to implement this next year. So I want to start to step back now, and I'm not going to talk much about these a little bit, but remember this cost function. If you put 100 ions in a trap, I think we can probably deal with all the motion of 100 ions. Imagine having 100 pendulums connected by springs. That's complicated, but you could imagine engineering the springs just right so that you could deal with that complexity. I don't think we'll be able to do that with 10,000 though. And so that cost function at some point is going to go through the roof. And we have to think about how to modularize the system, how to connect to another group of 100. If 100 is the magic number, put 100 here, 100 there, 100 there, and somehow couple them. Now, one model is sort of brute force. In fact, Dave Wineland and I and Dave Kopinski proposed this many years ago, and that is to make a very fancy set of electrodes where we sort of have the individual atoms surfing between different zones, in between computations. And, well, this is a nice PowerPoint ion trap. It's easy to have electrodes floating in free space. But in fact, there's a great deal of progress in making ion traps out of silicon. This is a chip, a centimeter on a side, that was built at Sandia National Laboratories, Georgia Tech Research Institute. It's a DoD lab in Atlanta is getting on board as well. Dave Wineland's group at NIST Boulder probably has the most complex trap. These are surface traps. The ions actually hover above the surface. And this allows you to pull the wires through the bottom for large-scale processing. So this is something, these chips, they're just starting to get used. Honeywell, I mentioned, and Lockheed, they're dealing and fabricating chips to do exactly this. I want to talk slightly bigger, and that is to scale over not just ions on a single chip, but actually communicating information from one chip to another chip, or two sets of ions that are so far apart that you wouldn't want to shuttle them. Well, it turns out we can also do this by coupling our qubits with photons. I just want to talk a few minutes on how that works. And the large scale, this is sort of a concept picture. The large scale here then is to take individual modules. These boxes might contain 100 or whatever your magic number is, 50, 10, 100, 200. And then have fibers coming from one or more of the qubits inside a module, and have optical switching networks allow you to entangle atoms between different modules. And this is a truly modular architecture. If you can make one red thing work, if you can hook up two red modules, you could think of hooking up 2,000 red modules. I don't know what the cost function is there, but it's not going to be exponential. Probably more like linear, maybe quadratic. I'm not sure. But well, that's a good question. What you're doing here is limiting the connectivity, because there's near full connectivity within a module, and here we're sort of, the weak link here would be maybe only 10% of these have an optical link. So you're right, this is important. There's overhead involved in getting complete connectivity. Maybe you need more modules. So these are really good high-level questions that I'm starting to learn about. Was there another question?
Could you ask that question, or just restate the question so people that are on air can hear what it was?
Oh, okay. You want to do it? Or? Okay. So the question was, in this modular architecture, is it fully connected? And the answer is no, it's not. Not as connected as the atoms within a module are connected. Those atoms can be very well almost fully connected. But these optical interfaces are sort of weak links, in the sense that not every atom in one module is connected to every other atom in another module. So this is a great compromise that I hope computer architects start to study. And I think this is true in any quantum architecture. We need to study these things. What are the trade-off spaces? What are the cost functions? But the important point, I think, the one word that is important is modular. Any quantum architecture has to be modular if you're going to make it really big and therefore useful. Well, let me now step way down, jump down off the cliff from the bottom, looking up again, and tell you how this mapping from qubit to photon works. And this is sort of the last I want to talk about. Well, here's our atom. If you remember, our qubit was stored in these two levels. Well, we can shine a different laser beam on a single atom. It's a fast pulse that puts the atom in the excited state. This pulse is on the order of a picosecond long. It's not hard to do that. And then what happens is, in the next 10 nanoseconds, this state is unstable. It will decay. In fact, it will decay along one of these two paths. It could decay back to where it started, but in fact, due to some tricks, that doesn't happen as long as you observe the light in an appropriate direction. It turns out to be along a magnetic field that you apply. And when you do that, now we have a single photon that was emitted from a single atom. And better yet, the polarization of this photon, denoted by sigma plus and sigma minus, this polarization, sorry, let me back up a little. This polarization is entangled with the internal state of the atom. But I didn't talk about this, but these two states are actually not so good. They're very noisy states. So when this happens, we immediately zap the atomic population with microwave fields. This is all very clean and very well established. We return the atom to the space of the qubit we want. And what we end up with is an entanglement between the atom's, the internal qubit state of the atom and the polarization of this photon. The trick here is that this photon could have been lost. Photons are tricky. They're not like matter. They don't hang around. They can hit walls. They can go all over the place. They can get lost in a fiber. They can hit a detector, and the detector won't fire. There's lots of loss mechanisms, and in fact, this is a very lossy channel. You can't collect all the light. So I say this is entangled, but it's a very weak entanglement. In fact, you can only say this state is entangled if you post-select it on the condition of knowing a photon is there. And we don't know photons there until we detect it and therefore destroy it. So this type of entanglement is actually useless. Typical atom-photon entanglement is useless when taken in isolation. In fact, the probability of having this state is only about 0.5% due to all these losses. We collect 10% of the light, 20% of that makes it into a fiber, 25% of that registers a click on a detector. So already 0.5%. But what's magic is if we do this twice, something cool happens. Well, we do it twice or we square it. So if this is 0.5% and that was 0.5%, well, the probability of getting 2 photons is 0.5% squared, which is really small, 10 to the minus 5 or something. But when we take those 2 photons and overlap them on a beam splitter, this is really getting into the woods here. When we overlap them on a beam splitter, it turns out this beam splitter erases which path. It erases the information of which photon came from which atom. And remember, the photon can be one of 2 different polarizations. So by detecting appropriate coincidence events, there are 2 photons, and so you wait till 2 detectors fire. And when they do, you've basically entangled these 2 spins. And the problem is it's really slow, because there's a repetition rate of the whole experiment. You're trying and trying and trying, but p squared is the probability of success. So in fact, this rate is it's painfully slow right now. It's on the order of 5 to 10 hertz. Really, really slow. Nobody wants a computer with a 5 hertz clock, right? So this is one reason I said that that link is weak. It's slow. And I'll show you what sort of the state of the art right now is that of this modular architecture. We have linked 2 modules with multiple ions in them. About 5 years ago, we were at 1 millihertz. That's really slow. You have to wait 10 minutes for a single click. That's no fun. Right now, we're at about 10 hertz, and we know how to get to the 10 to 50 kilohertz range, which is a lot better, but it's still, you might wonder, is it too slow? It's an open question. This experiment having 2 modules, this is what it looks like in the lab. And again, I'm exposing our basement university style here. Here we have 2 vacuum chambers, and there are fibers that come out from each of these. And in this setup, we indeed teleported the information from one qubit to another. Now, we could say we teleported the atom, if you want to use full license on that word. Well, the atom's personality is given entirely by the qubit. It's the same atom, same isotope. So if you actually teleported the atom like we think of Captain Kirk going from A to B, you wouldn't have been able to tell the difference. All we did is we moved the quantum information the unknown quantum information from here to there without destroying it. And that's called teleportation. It's a good, useful protocol for moving information around. But never think it will be applied to big things. Okay, single qubits, fine. Maybe 20 qubits, maybe 1,000 qubits, but not 10 to the 25 qubits, which is me. Okay, so and to see a back view of this same lab, you can sort of see the issue here. Those two vacuum chambers are right here, by the way. And all this other stuff in control electronics are devoted to the lasers that excite the atoms and allow us to measure the individual spin. Now, I don't mean to scare you here. It is kind of scary. Each piece of this table we understand fully, and each piece is trivial, but there are thousands of pieces. So 0.99 to the thousandth is still 0. So you have to, it's a real art to run one of these experiments. But there's just no question this thing can be miniaturized in a very big way. And this is something that hasn't happened. We have to have this happen in this platform. And we like to step back and think of the evolution of classical computing. I would claim that the physics between this device and this device didn't change. Now, people would object. There was beautiful material science that came from that, but the basic physics of a transistor is the same. But this looks ridiculous. You can't miniaturize that. In fact, if you slam the door shut on that lab, it wouldn't work. So now we have VLSI, of course. It's the miniaturization, the making the footprint smaller that we need. And the thing about atomic physics is that it hasn't been tried yet. Nobody has engineered these systems. I'm convinced it can be done. I don't know what the cost function is, but I know that the efforts in the next 5 or 10 years will at least tell us a little bit about how far we can push this type of vision. And again, I think I want to back up and say that this atomic view of quantum computing, it really is complementary to superconductors. I think superconductors have the edge in terms of right now being able to get chips. But the individual superconductors, the qubits, they're all a little different. And when you scale that system up, the calibration, not just in the qubits, but in the pairwise interactions, get to be a major part of dealing with the entire system. Now, we will have calibration issues with these atoms, not the individual qubits, but the lasers that couple them together. So some of those problems will persist. But the fundamental qubits themselves as a memory are, I would say, more fundamentally scalable than any solid state because they're atomically perfect. Okay, with that, this is a dated picture of some of the researchers in our group. And I point to 2 collaborators in particular, Phil, because he's here in the audience. He's about to go to the University of Indiana in the fall to start an ion trap lab, as are these 2 other postdocs. Brian is going to Lockheed in Colorado. Graham's going to Honeywell. So we're farming people out to do big things. I also point to a close colleague of mine, Jung-Sang Kim, who is an electrical engineer and a sort of an expert in MEMS and photonics and microelectronics. He's been doing atomic physics for 10 years now, and he has a systems level view of how to make things big. And I work very closely with him on this vision of building something in the next 5 years, 5 or 10 years, that hopefully can do an important problem in quantum computing. And I should also thank our funding source. Currently is in that big dome there. Okay, thank you for your attention.
So, are there any more questions?
Chris, so it seems like the basic clock time is one challenge in ion trap systems. Do you have any? So the computation has to be large enough to be able to make up for it through better scaling. And do you have any sense sort of at what problem sizes or for what problem types, and accordingly you would get ahead of classical method?
So the question concerns overall computation times, and I guess it's true that the gates that have been developed so far with ions are in the sort of the megahertz or sub-megahertz type range. Maybe 100 kilohertz is a typical gate speed. I guess two ways to go. There is research pushing toward much faster gates, as I mentioned a little bit. That's a little speculative. It requires a lot more laser power. If you want to make it go faster, you need proportionally more laser power, and that has its own problems. But even at 100 kilohertz, if it's a question between a computation taking 1 hour and 10 years, it's sort of obvious. But I guess I haven't spent enough time looking at problems and what, the Shor factoring algorithm is probably one of the hardest you could imagine. With fault-tolerant encoding, it probably requires 1 billion gates on 10 million qubits or something like this to factor an interesting number. So if you do 1 billion gates and each one is at 100 kilohertz, that's a problem. That's 10 to the 5 seconds. So I guess I'm sort of wavering. I'm not answering your question very well. I just don't know what, it depends on the size of the problem. I guess I'm heartened a little bit in the sense that if you build a device with 100 or 200 qubits, I don't know how many gates you would have to do to make something interesting with a few hundred qubits. It's probably some power of 200, not a huge power. I'm not sure. And if the numbers are on the order of 1 million or so, I'm not too bothered by that. That would be a 10-second computation. So you know much more than me about how complex optimization problems might be. If the state space is enormous, maybe this clock speed does get to be an issue. But I'll admit I guess I haven't thought about it as much. It's a good question.
Thank you.
Maybe that'll limit the ion traps to doing certain types of problems more accurately but slower, and maybe in the long run we'll have some hybrid approach where you have the fast processor and the slow one.
You were talking about the going into the low energy state in the antiferromagnetic order. One thing I wasn't quite clear on when you were bringing that state up was at the time you're doing the anneal into that state, which was sort of usually successful, but not as successful as you'd like because of the domain walls. Was that actually still a superposition before you measured it, or was it inherently in a single state long before you got to the point of having a look at it?
Oh, that's a good question, and we haven't done too many experiments showing the coherence between these two states. It turns out that to show, I should go back to this global picture. To show coherence between these two states, there's a way to do it. It's very well prescribed, but it requires very high fidelity preparation of that state. Basically, the fidelity has to be 1 minus 1 over n. So for 10 spins, it has to be at least 90%, and we're not there. So that most direct measurement we weren't able to do. Now, the group of Rainer Blatt at Innsbruck has shown coherence in a different system. He's shown coherence of up to, I think, 14 spins in particular states using that trick. And also, in a separate experiment, I didn't show the data, one sort of sanity check is to do this adiabatic ramp right here, and then before measuring, reverse it. Now, of course, we first do the experiment where we measure and we get the populations. But then we do the experiment again and we reverse it and see if we got the initial state. Now, if there were no superposition at this point and we reverse it, we will not get the initial state. It'll be noisy. And this is, most quantum experiments do this. They measure populations and then without measuring, you do something else to measure the coherences. And so for that experiment, we showed, I think with 10 spins, a fidelity of 70% reversal to its original state. So that indicates there is coherence there. It's very hard to say exactly how much. So these problems are really tricky with many qubits, showing many qubit coherence. But very good question, thank you.
If for the can you couple the spins when you couple the spins adjacently? Can you make it an asymmetric couple so that you can run that AFM crystal as a shift register and shift to the domain walls at the end?
Indeed, I skipped a slide where this shows you sort of a device where we hope to have arbitrary Ising couplings. It basically involves having individual intensities on each spin. And that allows us to have an arbitrary map And so you could just program it classically offline and decide what you want to do. Sure, shift registers, and you can do gates this way. This could be the adiabatic model. It could be a gate, just a discrete gate on any 2 spins, on and off, and so forth. So it's reconfigurable, very flexible. And I'll also say you're opening the door to noise. Anytime you have to focus all these atoms, all these beams on individual atoms, there are issues you have to deal with. And this is where a robust engineering approach is needed. But in general, yes, we're thinking about architectures where we do shifts, first in, first out type operations, and so forth with these ion chains. Thanks.
Thank you.